Hello, my name is Dániel Horváth, and I'm going to present you our work titled Sim2Real grass pose estimation for adaptive robotic applications. First, I'm going to talk about our motivations. Adaptive robotics plays an essential role in achieving truly co-creative cyber-physical systems, and in new generation intelligent manufacturing, we try to combine artificial intelligence with manufacturing science. And within artificial intelligence, we deal with deep learning-based models a lot. And for these models, we need a huge amount of data so it can be trained on. And many times in the industry, it's just not feasible or really tedious. So we need to somehow get this data. And our idea is to generate this data synthetically from a simulation and make it work in real life. Obviously, if we don't do anything, then it's not going to work. But our aim is to use domain randomization and other types of transfer learning to make it work in real life. So the Sim2Real grass pose estimation pipeline. This is the pipeline we came up with. And basically the input is an image and the output is the objects on the image detected, classified, and all of the 1D orientation of these objects. And it has 4 steps. The first step is the object detection, which is a convolutional neural network. In this case, we use the YOLO V4, but it can be any other types of convolutional neural network. And then we have a rule-based region of interest cropping method, which is not only crops it, the image, the objects from the image, but also transforms these images in a way that the orientation estimation models can use this as an input. And then in this orientation estimation, we have the cropped image of the objects, and for every class we have a dedicated convolutional neural network which basically finds the orientation of the given object. And we use the sine and the cosine of the orientation because we want to have a 360 degrees of estimation. And we also want to make these values to be continuous. Just a quick example, if we detect 0 degrees as an orientation, but the true orientation is 359, then if we don't use the trigonometric function, the loss value between these two values is going to be 359, not 1. And it was just easier to use a trigonometric function because then we don't have this kind of problem. So this is and these 3 steps is the real-time version of our multi-object grass pose estimation model. But and it's really fast. So the object detection model works 20 FPS, and the object detection and the orientation estimation works at 100 FPS. So it can estimate 100 images, the orientation of 100 objects basically in 1 second. But it had good results. I'm going to show you it a bit later, but a bit of fine searching for the good angle, good orientation could improve the performance. So we had a pattern matching, which is just around the optimal solution, or just around the orientation estimation solution. And with this, it's only 1 FPS, so 1 image per second. So it's basically, it really reduces the speed, but it improved the performance, and that's we call the high precision version of the multi-object grass pose estimation model. So firstly, I'm going to go through these steps, and then I'm going to show you how the flow of information works in the robotic system. And then I'm going to talk about Sim2Real transfer, and eventually I'm going to show you our qualitative and quantitative results. Third part is the object detection. This part is our previous work. So we were building up, this is the second phase of our research in this Sim2Real transfer, because first we had the work on purely object detection, and that was so I'm not going to go detail into this one. The main idea is that the object detection, we generating the synthetic images with the bounding boxes, we train the model, and then we use it in real life, and it is working. And you can see the details in this article. The next step is, but obviously for robotic grasping, we need the orientation as well, otherwise it just doesn't work. So we need the region of interest cropping first. That's the second step. in our pipeline. And then basically in an image, we have the bounding boxes. And then we crop the region of interests, and then we padding them to be a square. It's for our convolutional network is really important to be a square. And then we resize it to the size that it's acceptable by the convolutional neural network. So the orientation estimation, the third step, the input is an RGB image of the given object. As I told you before, we have one CNN for all the classes, and the output is the 1D orientation, which is basically two numbers, a sine and a cosine. And the model is a custom-made CNN. As you can see on the right side, this is how the structure of the CNN is. So the body, which is the feature extractor, we use convolutional layers with different kernel sizes, different depths, but all of them with the activation of a ReLU. We use max pooling as well. And at the end, we get a 2048 long vector as a feature of the image, feature vector. And then in the head, we use fully convolutional layers, four of them, to extract the information for the feature vector, to have two numbers at the end, which is the sine and the cosine of the orientation. And the fourth step, which is an optional step, is the pattern matching. Here we use 360 pre-computed kernel images. So it's previously computed, we don't need to do it on the fly. And it can be more or less depending on how much accuracy that we want. With 360, we have one kernel image for each degree. And so we have the real image, and we're comparing them to these kernel images, not all of them, but let's say within a neighborhood. And then we pick the one with the highest correlation. It works really well with the given framework, but it's important to note that we need a good starting value to make it work. So which is coming from our orientation estimation convolutional neural network. That was the 4 steps. I'm just showing you the pipeline once again. So the object detection, and the region of interest cropping, then the orientation estimation, and then the pattern matching at the end. And now I'm going to talk a bit about how the flow of information works in our robot. So we have a camera, and with the camera driver, we have an RGB image. And it's really important that I think it's really good in our work, not just that it's fast, but we don't need the depth data, which in robotics, many times it's really good, easier to use the depth image, but we were thinking, why cannot we do just with the RGB image? And so the orientation estimation gets the bounding boxing from the object detection and the RGB image. And here the 2 version, the real-time version, just straight away sending this information to the grasping demonstration node. But if you have the high precision method, we have a pattern matching, which is shown with orange. And so the grasping demo using the MoveIt as a fast planner and the Franca control. We also have a module to transfer from pixel coordinate system to the robot coordinate system. We had a calibration method before that to make it happen. And this is around it, the flow of information of the raw structure. And then the Sim2Real knowledge transfer is that you can see on the right side that how generated images look like. So basically we want to introduce artificial noise. This is part of domain randomization. And with this, the model will learn the domain independent representation of the objects and not going to overfit on domain specific details. And as a result, it's going to work in real life as well, and not only in the simulation. And you can see these kind of domain randomized images on the right when we rotate it in different angles to different objects. And obviously this blue line, which is the orientation, is not on the training image. I just put it there so you can see the different orientations. And yeah, we use different textures, different camera position, different lighting, and different sizes. And this is how we can make it. This is also how we randomize. And sometimes we use some post-processing method as well for the image to introduce further artificial noise to the equation. So the training, for the training, we use mostly these synthetic images. And for these results that I'm going to show you just shortly, we used 10 real images as well. We went for a safer approach, but according to our data, probably it can be reduced, maybe even to 1 real image. As in object detection, it works with only 1 real image. But for the pose estimation, we used now 10 real images, and the parameters can be seen on the top left. And I think I really like this graph on the right side, which is showing, so the ground truth with the sine and cosine, because the object is rotated around itself, so it's 360 degrees. And so the model needs to approximate this function. And as you can see, how the colors get darker. So basically the training in the later phase of the training, it approximated quite well. So it shows how it works and how it learned to approximate. And these data is from not from the training, it's from the test set. This convergence. So the quantitative result, on the left side, you can see the object detection, which is the MAP score. You can see from the training data set is synthetic, the validation data is synthetic, and the test data set is real life. So you can see there is a bit of drop from some simulation to the real life, from the validation to the test set, but it's not really a big gap. So the reality gap is reduced. And for the right side, for orientation estimation, what we see is that we have a synthetic and real training set here, and the validation set, which is synthetic, and the test set, which is real life. You can see that the result is also it's good, that we could reduce it. It reduced a bit. We could reduce the reality gap, even though the results reduced a bit. I think 97% is reasonably good. One thing which is maybe a bit of problem, or it's interesting to note at least, is that the arm, it only scored 92%, while the base and grip were 99% for the test data set. And we think the reason behind this, that the arm, which is the yellow one, is that really symmetric. So maybe sometimes the orientation was the other way. So it's like 180 degrees the other way. So this is something that we need to investigate, and we also obviously want to try for different more objects and want to have more exhaustive ablation study as well. But as early results, I think they are good. And some qualitative result for the left side, you can see an accurate example, and on the right side you can see an inaccurate example. As you can see on the right side, on the right image on the left side, the orientation is a bit tilted from the optimal solution. And for the robotic result, we made the robotic experiment when we needed to pick and place these objects from the starting area to the target position, and we achieved with the real-time version 80%, and with the high precision 96.67%. I would note that here is that this is the first step in this Sim2Real transfer methodology. So I think it's not, and in the state of the art, these results are really good, considered as really good, and we don't need to. And obviously, the second step would be to make this method as robust as it can be applied in the industry, which is 100% all the time, everywhere. But then for this, to try out this method with synthetic images, I would say it's good as initial results. And for the end, I would like to show you a little video about our findings. So basically, you can see how the object detection and the orientation estimation works in real time. And what's interesting here, the background is really like noisy, I would say. So many traditional computer vision methods wouldn't be able to recognize like this, and also, or would need to be trained on this specific background, and then in another background it wouldn't work. And here you can see how the robot can actually grasp and put down the objects. I'm going to show you this second example. Used here a Panda robot, but we also tried with the UR5 robot, and it worked the same way. The ROS architecture is really good for that we can just plug another robot and then it's going to work. And this was it. Thank you very much for your attention. Contact me if you have any further questions, and see you at the conference. Bye.